Okay, good. So hi everyone. Today we are happy to have Conghuan from USC to tell us an update on the 4D Yang-Mills Flux tube spectrum.
Thank you for the invitation and also the introduction. So today I'm going to talk about the story of 4D Yang-Mills Flux tube spectrum, which actually comes from lattice. So let's start with some motivation. So we know that Yang-Mills theory, the low energy actually develops a mass gap and exceeds linear confinement behavior, which means that background quarks are actually connected by flux tubes, and flux tubes are very in the macroscopic, they behave like strings. So presumably it can be described by effective strings, which is actually verified by lattice QCD. So in this work and this whole series of work, our goal is try to understand confinement, but from a very special angle. That is that we try to understand the dynamics on the wall sheet. In the large N limit, the reason we are interested in large N limit is because in this N goes to infinity limit, the string coupling actually goes to 0. So this flux tube don't interact with themselves, and we actually have a well-defined 2D QFT, which is UV complete. So the hope is that by studying this wall sheet dynamics, we can get some hint on what's going on in the bulk, like why we should have this confinement behavior. So let's see a summary of this work. Firstly, from the lattice data part, we have completed the Monte Carlo computations of the 4D SUN Yang-Mills theory, the exciting confining spectrum in that theory with the highest precision thus far. And from a theoretical point of view, we have also get the method of computing all the low-lying spectrum using analytic ways, and we have verified that all excited states we have observed on the lattice can be described by the effective string action with the introduction of a light massive pseudoscaling, which is sometimes also known as wall sheet axion, and I will use this name in the following. So the main focus of this work is that we find no other low-lying residences for the Yang-Mills flux tube, which in some sense probably surprising. But we also got to point out the point of view that why we expect it this way. And we also want to stress that we have this practically effective way called 3TD bar dressing technique, which is very useful of describing the low-lying spectrum of axionic states. So the outline of my talk today will be separated in these several parts. First, I will briefly review the lattice setup and mostly just to fix the conventions. And then I will reveal the effective string theory and how I'm going to compute the spectrum of this flux tube, of this low-lying flux tube spectrum from using theoretical method. And then we'll go to the main result of showing you some of this data and also how good our theoretical matches. And then go to summary. So first is the lattice setup. So for some reason, it does not show the whole. So we use the Wilson action, normal one with one coupling beta. And in 4D, we use cubic lattice with a periodic boundary condition. And also here, I show you some lattice parameters like the lattice size. And in this work, I will focus on confining strings that wind around one spatial circle. So it is protected by the one-form symmetry. And also we have 3 colors, n equals 3, 5, 6, where we computed the spectrum. And the table below, we show some lattice parameters in these simulations. And specifically, I want to emphasize that for n equals 3 and 5, we actually use 2 different beta, which means that we have 2 different sets of data in different lattice spaces. In this way, we can see how sensitive the spectrum is versus the lattice spacing. and like how close we are to the continuum limit. So the way we use to the formalism we use to extract the excited spectrum is called the generalized eigenvalue problem. To summarize, is that we start with a large basis of operators. Here we use Polyakov operators, which I just said is to wind around the one spatial circle, and then we try to include as many Polyakov operators as possible, which I have listed like the full set of Polyakov operators we have used in the simulations, and then we use some variational method, namely like some criteria to distinguish which linear combination of these operators will be a good probe to the low-lying excited states. And then we use this linear combination to build the wave functionals of the excited spectrum and compute the energy. So actually, yeah, there's one sentence below that we also use different mirroring and blocking levels to create operators. Namely, we want to use different Polyakov operators with different string width, so that we can probe the IR objects instead of just the pure line, which we know is like of the lattice spacing and not physical at all. So the quantum numbers we use to denote all the sectors includes the following. So firstly, this one form CN charge, and in this talk we'll focus on k equals 1. Well, and people are also working on the lattice spectrum, the confining spectrum with k equals 2 and higher, which may probably be interesting, but here because we are interested in the larger limit, so that will not provide any new perspective. And the other quantum numbers include the longitudinal momentum, which is quantized on the lattice because we have a finite volume. And the angular momentum, J, which is also known as spin, which is mod 4 on the qubit lattice because the continuous rotation is spontaneous. It's broken by the cubic lattice. And then we have two parities. So in the following, we are going to denote the sectors using the spin and two parities. And where we include non-zero longitudinal momentum, we will instead get rid of longitudinal parity because it does not preserve the longitudinal momentum. So this is one example of the spectrum. And here I include actually all 5 sets of data for n equals 3, 5, 6, and 2 different lattice spacings for 3 and 5. And we can see that, so this is the ground state, and the first excited state and second excited state. And the black lines I'm going to discuss more later is called the GGRT spectrum, which we kind of expect the string spectrum to be very close to it. Although we see that already in this case, the second excited state is has a large deviation, which I will go back. And another example, which I also show here, is the 0 sector. So it's like spin 0 with 2 minus parity. And here we also show a large deviation from the so-called GGRT spectrum. And yeah, I will go back to that later. So this is just give you a taste about what kind of lattice spectrum we have, and like how they look like, what's the errors, etc. So okay, let's review effective string theory. So in the effective string theory setup, we try to consider an infinitely long stable string, and the classical solution is just straight line, and this classical solution spontaneously breaks the d-dimensional space-time Poincare symmetry into a rotation group transverse to the string, to the string motion, and the rotation group on the string motion. And we want to describe the low energy excitations on the motions, and this is known to be described by d-2 Goldstone bosons which characterize the transverse oscillations of the strings. And this is true only in the assumptions that we have a bulk mass gap. So it is not conformal, and also it is below the scale of the massive modes on the string motion. And we will soon see later that the second assumptions will break down for the S1 Yang-Mills theory. But we still have a way to remedy this assumption. So the most general low energy effective motion action can be written down using the assumption that it should be preserving the repolarization invariance and also the d-dimensional space-time polarized symmetry. The point is that we can write down all the terms using these geometric quantities known as Riesing curvatures and also extrinsic curvatures, which are constructed from the induced metric, describing how a string motion is embedded in the space-time. So and then we can write down these terms order by order in the limit of the string length. So string length squares kind of the inverse of the string tension, which characterize the effective scales of this theory. And so if you look at the first few leading terms, we see that the most leading order is given by the Nabugoto action. So it says constant here. And then it's given by Riesing scalar and some combinations of the extrinsic curvature. And if we apply the equations of motion and also Gauss quadratic equation, we can see that all of these terms vanishes besides one topological term, which is irrelevant in the case that we only consider a straight string. So this is known as low energy universality of the static string theory, in the sense that the non-trivial terms only appears in the sub-leading order of the string action, which means that well, one good thing of this is that all the effective string spectrum are very universal. So the leading behaviors is general, that we don't really need to consider what specific theories we are embedding this string in. But the bad thing is that if you want to really study the specific theory, so the non-universal coefficients are very hard to extract because it is very subleading. So we kind of requires high precision in the lattice spectrum, and or probably some analytic ways of constraining it. But yeah, later I will also shed some light on in this direction of how to extract the universal contribution coefficients efficiently. So just as an example, given this effective string action, in principle, we can do perturbation theory. And this is historically known as derivative expansion. That is, we can just look at the Feynman diagrams that corresponds to those ground states and excited states and compute all of them order by order. And this leads to these expansions with the expansion parameter Ls over R, where R is the string length and Ls is so R is the string length and Ls characterize the string tension. But this is not very effective. It's not in looking at the excited spectrum, because firstly it converges slowly and it kind of breaks down very early for excited strings. So we are looking for a more systematic and practically useful way of describing string spectrum. So this comes to this well-known formula in the lattice community, which is known as GGRT spectrum, and it is written this way, where NR and NL are from the string spectrum perspective, it just labels the number of excitations of the left moving and right moving sectors of the string. And this formula Well, kind of surprisingly, like 10 years ago, that it agrees pretty well with the Monte Carlo data of low-lying states of autoconfinement closed strings in 3D and 4D, even when they are very short. It's surprising that because we know that it is already way beyond the regime where the direct expansion breaks up. So why does it describe so well? So firstly, this formula is analogous to the line concatenation of the critical string at d equals to 26. And if you just naively analytically continue that formula, you get this spectrum. But it is also well known that line concatenation is not compatible with Poincare invariance when d does not equals 26 and d does not equals to 3. So we know that this spectrum cannot describe flux tube embedding in this d equals to 4.
So when you say that the formula agrees well, for what dimension, for what you put in for d?
In practice, it agrees well with both d equals 3 and 4. That's where we have spectrum. For d equals 5, probably there are some simulations, but yeah, that's not very well started. And let's say because for d equals 5, the difficulty of doing lattice simulations is much more.
No, but you say that the formula agrees.
Yes.
With Monte Carlo. The Monte Carlo is for 4 dimensions.
Yeah.
So, but the formula includes d. So what do you put in for d to make it agree?
Also, yeah, you just plug in the space-time dimensions here.
So 4.
Yes, 4. And for and for three-dimensional space-time dimensional spectrum, we just plug in d equals 3. And this is supposed to work for arbitrary space-time dimension. Oh yeah, although we don't have much data for higher dimension. Yeah. So yeah, but yeah, the reason that is kind of surprising is because we know it does not it's not compatible with the Poincare invariance. So yeah, why it works so well? So the point is that this formula can be derived from, for example, applying the thermodynamic best answers on the worldsheet, which provides a systematic way of summing the conventional group expansions and gains better convergence. So I will briefly discuss thermodynamic best answers in the following, but not in details, just to introduce later the formalism of T-body formation. So the TBA, the short of thermodynamic best answers, is a systematic way of computing the finite volume spectrum for 1+1D system. That is it is given by the idea that if you know the 2-to-2 scattering, well, it is originally introduced to describe spectrum of integrable theory. So for integrable theory, you only need to know the 2-to-2 scattering. But in fact, it also works pretty well for non-integrable theory as long as we only consider excitations that involves 2-to-2 scattering. And this is given by a series of equations that I list here. But point is that these equations are in general very hard to solve. And it becomes even harder when in this case because we have massless excitations. But a good thing about confining strings is that it is shown that winding corrections only receive non-negligible contribution from leading order phase shift, which is verified by Sergey, Victor, and someone here. So the point is that the winding corrections are the most complicated ingredients here, and which will in general lead to integrable equations that is hard to solve. But these assumptions basically will high reduce the complexity. So we reduce these winding corrections into something that can be described in a closed form. Well, I probably should have mentioned what is the phase shift. So yeah, let me first remind you that the phase shift of the flux tubes in 4-dimensional spacetimes. Well, in 4-dimensional spacetime, we have two flavors of Gauss-Norm bosons. characterizing two transverse direction, and we can diagonalize the 2-to-2 scattering of these photon scattering channels into three different ways, which is characterized by the O2 representation. So O2 is the symmetry of this wall shift theory that characterizes the rotations transverse to the wall shift. So in these ways, we can get three diagonals scattering channels from which we can compute the scattering phase shift perturbatively from the effective string theory. And this is the result. And the leading order phase shift I just mentioned is this phase shift that actually leads to the GGRT spectrum if we start from this leading order phase shift. And this is a very well-known model that gives you a two-dimensional integrable model, which is just the TD body formation of free bosons. And yeah, so yeah, chronologically I should also first discuss TD body formation. But so the TD body formation is given is that if you start from an arbitrary two-dimensional QFT, we can consider the operator given by TT bar, and the deformation of this operator will generate a family of theories labeled by MD scale. In our case, it's just labeled by the string scale. And the finite volume spectrum is exactly solvable in the sense that if we know the original spectrum completely, we can use these differential equations to solve all the spectrums of this family of theories. So originally, this TD bar deformation is used only for integrable models where we actually know the spectrum at one point. But this the idea of TD bar deformation is actually very general. And the reason why TD bar deformation is related to thermodynamic backbenders is because another way to understand TD bar deformation is to look at the flat space S matrix, but the S matrix on the motion of a 2D QFT. And the TD bar deformation modifies the F matrix in a controlled way. That is that it only stresses the S matrix by this integrable phase shift. So if you start with a theory without the integrable phase shift, we can actually use the TD bar deformation to plug back in this phase shift. So this leads to the following strategy of computing spectrums of combining strings for Yang-Mills theory. That is, we can first start with the wall shift theory without the leading order phase shift. That is to say, we start with all the phase shifts here, but we throw away the leading order contribution. And because all the rest of this phase shift is kind of splitting, they're very small, so we can use the asymptotic backenders to simplify the thermodynamic backenders. So asymptotic backender is just the momentum conservation here with the insertion of the phase shift, and we see that here we have completely thrown away the winding corrections of the thermodynamic backenders. And this is just some algebraic equations we can be solved very easily. So with this asymptotic backenders, we get the spectrum of some theory that does not have the integrable phase shift, and then we put back the integrable phase shift by doing TD bar deformation to the spectrum we obtain using these formulas. So this is like a systematic way of simplifying thermodynamic backenders. Yeah, so that's the introduction of previous how people do spectrum computations. And well, that's just a background, because here later I'm going to introduce the kind of another version of this TD bar deformation, which allows us to compute theory effective string series that contains massive modes. So after the review, I will go to the main results. So in what follows, I will focus on one special parameter, which is n equals to 3, nc equals to 3, and with the smaller lattice spacing. The reason I focus in this case is because this is the data we have highest precision, because we have smallest column, which allows us to do the largest sample size. And also because of the small lattice spacing, this allows us to extract hairy states. The reason that we can extract hairy states with finite lattice spacing is because it's like in lattice we generally compute the spectrum used by looking at the correlation function of 2-point functions. And this 2-point function kind of decays exponentially. So we want to, while it decays exponentially, but the noises of the Monte Carlo simulation is kind of a fixed value. So it will decay very fast into the noises. So we want to extract it before it goes to be drowned by the noises. And the way is that we add more data points doing this exponential decay, which is given by, well, this is achieved by using finite lattice. So this is one example where we have lattice data for SU3 and beta for smaller lattice spacing, and I'm focusing on the the cases where we have excitation on the strings with 2 phonemes, like just NL equals NR equals to 1. So in this case, we have 3 different states corresponds to, well, 4 different states corresponds to 3 different channels. And I use different colors to label them in blue dots, in brown dots, and light green and dark green dots. The red line is the so-called GGRT spectrum, which is what we expect it to be close by. Of course, there are higher order corrections, so it will not be exactly the same. But we see that although the brown dots and green dots align pretty well with this red line, there is the completely outlier, which is given by the blue dots. And these blue dots are the spectrum in the 0 minus sector. So like both parity minus. And here I show you the spectrum where I have subtracted the ground state energy. So we see that these blue dots are almost horizontal, which is characteristic of a massive particle. And later we see that it's definitely the case. And here I also show you the derivative expansion given by this dashed line, and we see that, well, the prediction is very bad and kind of breaks down for relatively long strings, so it's not effective at all. So the point of showing this figure is that we see that for 4D Yamil's theory, we actually see a obvious outlier of this string spectrum, which kind of predicts the existence of a low energy massive modes in this 0 minus quantum number. So to remedy this effective string theory, we need to add the massive pseudoscalar to the effective string theory, to the effective string actions, and it should couple to the Goldstone bosons in the following way, so that it preserves the Poincare symmetry. So here we have added this topological invariance of the coupling between phi and phi is the pseudoscalar, and the coupling to the Goldstone bosons, which lives in the extrinsic cavity. And this is like the leading order behavior, and there are sub-leading terms. As long as you can write down as many as you can, as long as the term is explicitly point carrier invariance. And this introduction of the action actually introduced an extra contribution to the 2-to-2 phonon scattering phase shift. So this is the corrections to the phase shift I showed before here. So this is the phase shift without the introduction of the massive mode. And after introducing such massive mode, we will have corrections to this phase shift, which is given by this form, where here I use the compact form to label all three channels using sigma 1 and sigma 2. And the sigma 2 is the summation of the resonance, because around on the P plane there's actually a zero, so where the perturbation theory breaks down, and we need to resum all the contributions. So after introducing this phase shift and we use TBA, we actually get a much better predictions to all three channels, which is shown here in blue line, in orange line, and in green line. So this kind of indicates that we are going the right track. So after introducing this worldsheet axion, and we actually only use two parameters. So one parameter is the axion mass, and second parameter is the axion coupling. And these two parameters are enough to predict, at least in this case, all the spectrum with n with level 1. Okay, so this is already good. And as a side, I want to point out the fact that the axion coupling that I have here, 0.37, with some systematic error, actually has a very interesting numerical coincidence known as triple coincidence. So this axion coupling actually coincides with the integrability value for one pseudoscale. That is to say, if you want to start from d equals 4 worldsheet theory, that is with two mass-based Goldstone bosons, and you want to ask this question, like, how do you want to make this theory integrable? Well, you know, with only two mass-based particles, not integrable. But this is the integrability can be achieved just by introducing, for example, one pseudoscalar, which couples to the mass-based particles with some couplings that can be computed exactly. And here is given by approximately 0.373. And we see that surprisingly, they match very well with thin error. And moreover, the same value of axion phase shift also appears when one do the flux tube F matrix bootstrap on the worldsheet theory. And so the point is that if you try to apply low energy point carrier invariance, and you try to use this to bootstrap the possible phase shifts, you get a boundary, which is we actually see that the coupling also lies on the boundary of this bootstrap result. And so this coincidence leads to the so-called axionic string atlas, which is the conjecture that probably integrability is restored at high energy for 3D and 4D flux tube vortices theory. Well, at this point, it seems quite surprising why this should be true, because we only started from the integrability. We only start from this coincidence between the axion coupling value and the integrable value. But one way that hint that this might not be too crazy is that we do expect that the degrees of freedom at IR and at UV to be to match each other. That is to say, in the UV we know that it is described by Yang-Mills theory with gluons. So we can start from a Polyakov operator, which is like just the analog of the Wilson loop, and then we can insert gluon fields on the Polyakov operators. So for 4D, for example, there are two ways we can insert the gluon fields. The first way is that we insert F IA, where I goes along the string motion and A goes. So I goes transverse to the string motion and A goes along string motion. And here we get so there are two possibilities for this. And this corresponds to Goldstone bosons on the string motion. And we actually have another possibilities where we have both directions goes in the transverse direction. And we do expect this to have correspondence to the pseudoscalar. Well, they have the same quantum number. So we do expect the degrees of freedom of a flux still motion to match at IR and at UV.
So what is that?
Oh, F is the gluon field, the field strength. The like where write down the action of the Yang-Mills theory.
The algebra valued one.
Sorry?
The algebra valued one is so next three is what you're saying.
Well, well, you guys think about it as a matrix here.
Yeah, so the left hand side is matrix and the right hand side is also a matrix.
Oh, you. I mean, because when you insert operators on the Wilson line, you want to make it gauge invariant.
So you're saying this is that's F of the Wilson line of this thing.
Yeah, I mean, when I say this, I'm actually thinking about lots of operators. So historically, I'm considering a Wilson line with some insertions of these operators. Yeah, so sorry, this is a bit too schematic. But the point is that when I insert these operators, all the possible operators I can insert here corresponds in number to the low energy excited states of the wall sheet. So like this is the UV picture. This is the IR picture. And here I have excitations of phonons. Okay. So what I have said before about the n equals 1 state is something we all people have already computed probably like 10 years ago. But at that time, we only have such excited states, and now we have much more. So we have like much larger families of excited states that we want to match. And the motivation is to have all this data is we want to ask this question, like, are there any other resonances in this low energy regime? So to answer that question, we need to first within our formalism of this one Walsh action, can we describe all the states in this all the low-lying states we have observed? So we want to find a way to compute all the axionic states. Means that all the states with massive excitations. And in general, it is hard to directly apply the TBA to these general states with more than 2 phonon excitations, because we know that the Walsh's theory of flux tube is not elastic. So there are mixings given by this sextic term of phonons, which leads to for example, particle productions. And well, at this moment, there's no systematic way of diagonalizing the whole S matrix. So in general, it is hard to do the first objective. But in this case, we are actually more interested in computing states with massive excitations. So here we propose a way of computing all these axionic states. That is, we use the following approximation. We start with the Walsh's theory of phonons, which interact only at sublinear ordering, low energy limit. Means that we have thrown away the leading integrable phase shift, and we also include massive particles. So here there's only one particle, which is given by the Walsh axiom, and we compute the finite volume spectrum of this theory using the asymptotic methods. And then we deform this whole theory by TD bar deformation to the screen scale, which will automatically, we hope, will automatically incorporate the leading order axion interaction and axion phonon interaction. And it turns out to be true. And we also, later I will present an argument why we expect it to be true. But at this time, it's mostly like just the ansatz for computing the spectrum. And we see how good it works, how well it works. So, for example, here we look at the flux tube spectrum with 2 massive excitations. This which is given by this blue line. Essentially, you're just looking at 2 pseudoscalars sitting on the Walsh at rest. And this is in the sector with 0 longitudinal momentum and also 0 spin, with both parity flux. And here I show you 2 different theoretical predictions. The first one is the dashed line, which I only include 2 free massive excitations with no interactions at all. And the second one is the prediction of after. So we have these free mass particles, and then we do the TD bar deformation. And we see that the TD bar deformation captures very well of this interaction, especially at this low string regime where we have much better precision. So this indicates that in this case, in this sector, the TD bar deformation of the string action captures very well the interactions between axons. And another example here, well, also a kind of trivial one, is that we look at the axion at rest and another Goldstone boson that shooting at it. So this is in the sector where we have one quantum of longitudinal momentum and also spin 1 given by the phonon. And here we also show you the 2 predictions. One is the completely free spectrum given by the dashed line. And the second one is where we incorporate the interactions using T-bar deformation. And we also see that here the T-bar deformation captures very well the interaction between the phonon and the axion at rest. And the third example, which is a bit more non-trivial, is we consider one phonon and one axion that collide with each other. Here there are two states in this scattering channel, which are labeled by light red dots and dark red dots, and we see that they are actually non-degenerate. So there's a split between them, but the T-bar deformation actually cannot predict this splitting, and we will see later. We will later give an argument why this is the case. But we see that here, the interactions still capture very well by T-bar deformation, given that we see that the interaction is very large in this case. So the dashed line is completely off, and the short red line is still pretty close to all the data points we have, while it cannot predict the splitting. So after showing you all this data, I'm going to give you a pedagogical argument why we expect T-bar deformation to work, and also why it doesn't work for the last case. Yeah, there's a line in the bottom. So the T-bar deformation with two massive particles and two massless particles and one massive particle is given by this formula up to O to the m squared order. And here the induced matrix is given by the original phonon induced matrix with the inclusion of one massive particle. So life is effectively like three-dimensional. Well, it's literally like the string sitting in the five-dimensional space-time. And from this action, we can actually work out order by order what kind of actions we have, order by order in terms of the string scale. And we soon see that it cannot be the complete string action, because this action does not preserve Conghuan invariance, in the sense that it is missing one term here given by phi squared dy squared. So it should be dx squared type. So this term is missing in this T-bar deformed action, and as a matter of fact, this is the term. This is exactly the term which leads to the splitting I just mentioned above, to these two scattering channels. So it matches very well with the prediction, because we see that this term has does not contribute to the other two cases where we see that the scattering, the interactions are described very well by T-bar deformation. So here for one close to boson and one axion, and also the two axion cases, we can see that this term actually vanishes. So in most of the cases, this term does not contribute. So we do expect this T-bar deformation to make very good predictions to the string spectrum. And also, as a good bonus about this exception is that we can actually use the splitting we observed above here between these two scattering channels to actually compute the non-universal coefficients in the axionic effective string action. So for example, so we know that besides the leading order non-universal interactions in the form of phi xx, there are also another non-universal interaction of like phi kk. So this will lead to some non-universal terms. So the splitting here actually gives us a way of computing the non-universal fractions to the effective string action. But although we also see that at this because it has very high energy, so the data is has kind of large errors. Especially here, we also see that there might be some systematic errors that are not accounted for in this by this error box. So while we do hope that in the future we'll have better data to resolve this splitting. So one thing. So one last thing I want to mention here is that in this work we also try to probe the higher momentum regime of the scattering, which is given by this spectrum, the first excited state of the 0 sector, which I show here in red dots. And as you can see, this also has very large deviation from the black lines, which is the GGRT spectrum. So so originally we want to ask the question why it has such large deviation. The problem of the solution I want to solve this is to add higher order corrections to the phase shift. So here we know the leading order term of the phase shift and also the one loop correction, as long as the result corrections from the resonances. And on top of that, I also use two more parameters with cubic terms and quadratic terms to fit for this data, to fit for this phase shift, and it works very well in this sector. This indicates that the momentum here is too high, so that we kind of actually need to add some more non-universal terms to the phase shift to actually account for the scattering. And here I also use two parameter fittings. And one good thing about this fitting is that it actually predicts another sector, which is kind of the boosted version, given by one longitudinal momentum with also parity minus. And the first excited state, so the red dots are just the boosted version of one axiom, which is not very interesting. But the blue dots here are the boosted version of the first excited state I just showed above. So the boosted version of the red dots here. And we see that with exactly the same fitting parameter, this gives a good predictions to the states here. So as a cross check, we see that the fitting for phase shift at high energy works very well for all the data we have. So why are we interested in the high momentum regime of the phase shift? So one thing is that we can actually use this higher momentum phase shift data to extract non-universal Wilson coefficients using dispersion relation. So that is kind of one effective way of extracting non-universal Wilson coefficients of this effective action. Okay, finally, I'll go to summary. So in this work, we have shown that like all the low-lying confining string spectrum in the 4D unwheels theory that we have observed on the lattice can be described by the formalism of effective string action with the introduction of a vested axiom. So we don't see any more actual low-lying excited states, low-lying massive modes, which agrees very well with the axiomatic string answers, saying that we only have enough resonance, like matter content in the flux tube to make it integrable in high energy. So one way to further verify or disprove this conjecture is that we can try to improve our calculation of the axion coupling. And also we can think about a joint QCD where the axion coupling will be changed accordingly, but in a controlled way. And another point that we have verified here is that the interaction which involves axions on the string motion can be approximated very well by T-body deformation. And we gave an argument why this should work. And we also see that the deviations are also appear in a controlled way, which actually allows us to extract the non-universal coefficients of this effective string action. And finally, I also point out that one possible direction is that we can use the high momentum data to provide measurements for the low energy Wilson coefficients. Okay, so I think that concludes my talk.
Questions from people?
So you didn't quite say, but does the agreement change with the values of n? You had a few values like 5, 6.
3, 5, 6. Good. Right. That's a good question. So as a we actually measure all these parameters for these 3 different values of colors, and it turns out that the axial mass will change. Like it will get lower and lower when you approach the large n, but it will kind of stabilize to a non-zero value, probably somewhere around 1.6, while the axion coupling is it's not very sensitive to the color. Although we don't have a very good measurement of the coupling also for higher color as well. Yeah, that's so actually it's also interesting to study to get a higher precision measurement of the axion coupling for a larger color. But it hasn't been done yet.
So you had a comment there that the axial coupling changes when you add joints.
Yes.
Have you actually done that?
I think people are engineers, for example, producing data for a joint QCD. But yeah, I'm still waiting for the data. So they're doing the simulation, but it takes so Monte-Carlo simulation takes very long time.
You mean just a joint one, just one joint, like super angles?
I don't think they in this setup they probably don't introduce supersymmetry, but they do add more than one adjoint. I think they add quarks, both fermions and bosons.
Who's doing this?
Sorry?
Who's doing this?
Andreas Anton Lore. Yeah. He mentioned to me that he's kind of having some data, but probably it's still coming out. Yeah, so this is actually a really interesting point because using the axionic string answers, we actually predict how the axion coupling will change in terms of this adjoint method. So that if we can successfully measure the axion coupling.
What's the prediction?
So the prediction is as the following. So the axion coupling is the integrable axion coupling is the coupling such that we resume high energy integrability. So that will correspond to a prefactor that is the same as the prefactor of the QCD beta function. And we know pretty well how the QCD beta function in the UV changes when we add adjoint methods. So yeah, that's the prediction.
What's the argument for that?
Well, so I think this is one of the pedagogical way to see why, but that's a conjecture. So, like, if you believe in high energy integrability, then it should be the case because you want to cancel the Poincare anomaly at low energy. So you must have the QCD. So you must have the axion coupling to be exactly at the integrable value. But if the high energy integrability is actually not true, then
No, I just don't understand the relationship between integrability and the QCD beta.
Oh.
But you said that there was a unique. You said there was a unique value of the coupling with 2 scalars and 1 axion.
Yeah.
That made it integral. So how could it depend on the beta function?
The beta function is no, but if you add a joint matter, then this is a new ingredient that will change.
No, but you're adding a joint matter in the bulk. It might not add anything on the world sheet. How do you know?
Why not? So I think adding a joint, so you can add these excitations of this joint.
But it doesn't. This is not a proof of anything. These excitations may be bound to the world sheet, or they may not be bound. This is like writing down the operator phi squared and saying it should create a bound state of 2 phis, but it could also just create 2 phi. So it's a dynamical question of whether these operators are like bound states on the string or they're just, you know, 2 particle states. So yeah, you can insert all the adjoints you want, but they may or may not be bound.
Yeah.
In supersymmetry, it's more sensible to expect that there will be something there, right? Because there'll be super partners.
See. Yeah, let me think about this. Thank you. Yes.
So consider a higher analytic string, so k not equal to 1, k 2, 3. You expect the mass of the axion and the EXX and the axion coupling to change. K.
Well, in that case, it's not because it's not fundamental. So you actually expect there are more resonances than just this one. So, but you can, of course, you can still find exactly the same resonance here with the same coupling, but in general, because there will be some like bound states between the strings that one can observe. Yeah, so with high analyty, well, the picture will not be so clean. I think there will be multiple resonances.
Has it been analyzed? Is this a conjecture or is it known?
So there are measurements of the k equals to 2 strings where the point is that the data is not so precise. I figure there could be some resonance, but I cannot be sure because there are too few data points to say anything at all. Yeah, because the k equals strings is harder to analyze because there's a very short window of the string length where you can have reliable data.
And for IC3 it cannot be.
Sorry?
For IC3 there cannot be additional resonances with the k equals to.
For SU3, there cannot be
additional resonances for k equals to. Because k is just a charge conjugation.
Oh yeah, no, yeah. I'm talking about SU4. So I think the data is for SU4 and SU5. Yeah, SU4, SU5, and SU5. Yeah, but the axion is kind of analogous in that sense. So the coupling is the same, mass is a bit different.
Should thank the speakers.